In electrochemical cells, the free energy of the redox reaction causes electron flow from anode to cathode. The reduction and oxidation reactions take place in separate compartments called half cells, which are connected to each other by either a salt bridge or a porous partition. There are different types of half cells or electrodes, as one may say. Number 1. Metal-metal ion electrode. Here, a metal strip is dipped in a solution containing the metal ion. The reduction and oxidation reaction take place at the interface of the two phases. Number 2. Metal amalgam metal ion electrode. Here, metal amalgam strips are used instead of pure metal strips, just to lower the activity of the metal. All the other features remain the same as that of the metal-metal ion electrode. Number 3. Gas electrodes. It contains an inert electrode like platinum in contact with a gas like hydrogen and a solution containing ion of the gas element like H plus ion. The hydrogen electrode at standard conditions is called the standard hydrogen electrode, or SHE. The free energy change of this reaction is zero because free energy of formation of both hydrogen and H plus ion is zero. So this reaction is at equilibrium and the reduction potential of SHE is taken as zero by convention. That's the reason for coupling SHE with different electrodes and measuring the cell potential thereof in order to calculate the standard reduction potential of the electrode with which SHE is coupled. For example, when SHE is coupled with copper-copper ion electrode under standard conditions, the SHE acts as anode and the cell potential is measured to be 0.34 volt, which is calculated to be the standard reduction potential of the copper-copper ion electrode as well. When SHE is coupled with zinc-zinc ion electrode under standard conditions, the SHE acts as cathode and the cell potential is measured to be 0.76 volt. The standard reduction potential of the zinc-zinc ion electrode is calculated to be minus 0.76 volt. The standard reduction potential of electrodes, or simply the standard electrode potentials, are listed in this table. It should be noted that while measuring standard electrode potential of an electrode, it should be coupled with a reference electrode of known electrode potential. SHE is not a perfect reference electrode due to the following reasons. It is better to use saturated calomel electrode as reference electrode for this purpose. Number 4. Metal insoluble salt anion electrode. In this type of electrode, a metal rod and the insoluble salt of that metal is kept in contact with a solution containing the anion of the insoluble salt. For example, silver chloride KCl electrode. The redox reactions are like this. And the mercurous chloride KCl electrode, also called the calomel electrode. The redox reactions are like this. Number 5. Redox electrodes. It contains an inert electrode dipped in a solution of two salts of the same cation but in two oxidation states. This electrode is dipped in a solution containing both ferrous and ferric salt, and this one is dipped in a solution containing both stannous and stannic salt. The redox reactions are like this. In all the electrodes, both oxidation and reduction reaction may take place. Now the question is, which one will take place, oxidation or reduction? The answer is very simple. This will depend on which electrode it is coupled with. The one having higher electrode potential will act as cathode and reduction will take place at that electrode. The other electrode will act as anode, where oxidation will take place. Consider the half reaction of the Voltaic cell at the cathode. The reaction proceeds in the forward direction spontaneously. Therefore, it is expected to show positive potential across the liquid-solid interface of the electrode. But for spontaneous reaction, the free energy change of the reaction must be negative. The Cu2 plus ion concentration gets diluted and a stage comes when the reaction reaches equilibrium. that is the rates of the forward and backward reactions, become equal. When not in equilibrium, delta G, the free energy change of the reaction, is equal to the free energy change at standard conditions plus RT ln Q, where Q is the reaction quotient. At equilibrium, delta G is equal to 0 and the free energy change at standard condition is equal to minus RT ln K, where K is the equilibrium constant. Now this free energy of the reaction is responsible for electron charge flow in the half cell. For 1 mole of copper deposition, 2 moles of electronic charge flow is required. The work done will be equal to electrode potential in volt, which is joules per coulomb, multiplied by the charge flowing in coulombs per mole. Here N is the number of moles of electrons involved in the half reaction and F is the charge of 1 mole electron, which is called Faraday and is equal to 96500 coulombs approximately. This work done is due to the free energy of the reaction and will be equal to delta G. The negative sign shows that the reaction is spontaneous. At standard conditions, the equation will be this. Substituting these two equations in this equation, we get this. The first equation is the preferred one. This is called the Nernst equation for electrode potential of a half cell. We further simplify the equation like this. Now we know that for Voltaic cell, the cell reaction is this. Reduction potentials are like this. Substituting these electrode potentials in this equation, we get the cell potential, which is called the Nernst equation for an electrochemical cell. At equilibrium, the cell potential becomes 0 and Q can now be replaced by K, the equilibrium constant. Here N is equal to 2. So if we know the standard potential of the cell, we may know the equilibrium constant, or otherwise if we know the equilibrium constant, we may calculate the standard potential of the cell.